Hello team, I'm Kundan Chapagai and this is my solution for the data synthesis machine learning task second round. In this video, I'll be explaining all four questions covering both algorithm design and the relevance in real world machine learning system. Let's begin with the first question. The first question asks how to efficiently return the sum of all values within a given range in an ABL tree. Here's how the algorithm works. We start from the root node. If the node's value is less than L, we skip the left subtree since all these values are smaller. If it's greater than R, we skip the right subtree. Otherwise, if the node's value is within the LR, include it in the sum and records the both subtrees. To make this faster, we can store the subtree sum at every node. So if an entire subtree lies inside our range, we can return the pre-computed sum directly. You can see the pseudocode here. For example, in the tree shown, summing values between 15 and 40 gives us 150. The time complexity for this is O log n in the best case when soft-tree sums are used, and On in the worst case when all nodes fall within the range. From a machine learning perspective, this concept is used in real-time feature aggregation, where numeric features like engagement counts or rolling averages must be updated quickly. Each tree update automatically adjusts the corresponding feature sums, ensuring that the downstream models always get up-to-date aggregates efficiently. Finally, this method also enables real-time roll-up feature in streaming ML pipelines, reducing redundant recomputation every time a data point changes. The second question is about storing and retrieving large model weight files distributed across a database using a B-tree. A B-tree is a balanced multi-way source tree where each node can hold multiple keys. Keys are sorted within each node, and all leaf nodes stay at the same level, ensuring balance. This structure is ideal for database and file systems where minimizing discretes and maintaining sequential access is critical. Because it's block-oriented and cache-friendly, B-trees scale extremely well for massive datasets. In a machine learning context, this is very similar to how feature embeddings or weight files are stored in production systems. For example, recommender systems often organize user and item embeddings using structure inspired by B-trees. This ensures that even when embeddings are distributed across servers, we can quickly look up, insert, or update vectors in O log n time. Here is how it works. Searching for a key takes O log n time because each node acts like an indexing, guiding us toward the correct leaf. Insertion is also O log n. If a node overflows, it splits and the middle key moves up. This keeps the weight low and guarantee predictable performance. Additionally, in distributed setups, each B-tree node can be placed in a separate shard allowing parallel access and horizontal scalability, which is essential for large-scale recommender systems. Our question asks for an algorithm to find a minimal spanning tree in a distributed system. We can use a distributed version of Boruksa algorithm. Here's a high-level process. Initialization. Each machine starts with its local vertices as a independent components. Find minimum outgoing edge. Each component find its smallest edge connecting to another component. Communicate and merge. Components exchange their chosen edges and merge those that are connected by the minimum edge. Repeat. This continues until there's only one component left. Result. The chosen edge together form the MST. The time complexity is O E log V. Overall, with about O log n communication rounds in distributed execution. In machine learning, MSTs are especially useful for feature clustering and sensor network optimization. For example, in IoT-based ML system, MSTs help minimize communication cost between sensors by ensuring data travels through shortest possible total path. In feature engineering, MSTs group similar features together, reducing redundancy and improving model efficiency. In large-scale ML graph construction, like similarity graphs or embedding clustering, distributed MSTs significantly reduce communication overhead while maintaining minimal total connection cost. The final question compares slab allocation and garbage collection as memory management strategies in memory constrained ML system. Let's break them down. Slab allocation. Memory is divided into fixed size blocks or slabs. Each slab is reserved for objects of the same type like tree nodes or graph edges. This approach is fast, predictable, and minimizes fragmentation. Allocation and deallocation are both O1. The downside is potential memory waste if objects don't perfectly fit the slab sizes. Garbage collection. Used in languages like Java, Python, and Go, it automatically reclaims unused memory, which simplifies coding. However, this introduces unpredictable latency due to cleanup pause and can increase GPU overhead. Allocation is O1 amortized, but the collection phase can take ON in heap size. For the comparison, we have compared the slab allocation and garbage collection on the basis of features like allocation speed, memory predictability, fragmentation, flexibility for object sizes, latency predictability, suitability for memory constrained systems. So, which is better for real-time ML system? Definitely slab allocation because it provides deterministic latency, which is crucial for online solving or inference. GC-based systems are better suited for offline training workloads where occasional delays are acceptable. In modern ML infrastructure, for example, solving engines like built in C++ or Rust, slab allocation ensures predictable low latency inference, whereas GC-based environments like Java or Go may cause unexpected slowdowns during garbage collection. To summarize, we explored AVL trees for efficient range queries and real-time feature aggregation, B trees for scalable indexing of large model weight files, distributed MSTs for optimizing communication and feature clustering in large ML systems, and memory management strategies ensuring predictable latency for online solving. Each of these algorithms and system concepts contributes to the efficiency, scalability, and reliability of modern machine learning pipelines, from data preprocessing to real-time inference. Thank you for taking the time to review my submission for the data synthesis ML task. I look forward to your feedback and to progressing to the next stage of the recruitment process.